Yes, good morning, students. Yes, am I audible? Hello.
Good morning, sir.
Yeah, good morning. So I'm audible, no? Okay. Hmm. Yes, Suhas Reddy, can you just brief me what we have discussed in the previous class? Suhas Reddy.
So 1 minute, sir. Recalling.
Okay, recall. Yes, in the meantime, others can also say nothing wrong. Only Suhas Reddy need not. Whoever was there, I think if they are able to say what we have discussed in the previous class, just I'm asking the topics. Yes, quickly, without wasting much time, let us start. Yes, Dharma, can you say?
Sir, modeling broadband of fading channel, sir.
Okay, so we have discussed about the modeling of broadband fading channels. Fine. So, is it possible to say what are the different models we have discussed?
Sir, one is Rayleigh fading and
Ah,
the other is Bayesian distribution, sir.
okay. Sorry. So, as I said, there are two ways to do. One is statistical modeling, and another one is the empirical modeling, right? So, under statistical, we have discussed three models. One is Rayleigh fading, second one is Bayesian distribution, and third one is Nakagami, right? Nakagami M fading. Okay. So, I said in empirical, Hata model is there, and how that data model is used for this LTE also. There's a discussion. We'll come back to that after some time. So today let me discuss about the mitigation of narrowband fading and broadband fading. Okay. So this is an important topic. What I wanted to say. Definitely there will be one question on this topic for your final year university exam. Definitely there will be one question. Okay. So there is a, please be attentive and try to understand what I'm saying. So first let us have what are the different techniques, right, for mitigation of narrowband fading. So for avoiding the narrowband fading or to mitigate, these are the four different techniques which are widely used. So one is spatial diversity, we say. Okay. I think I discussed in brief what is diversity and other things, right? So I expect you people to say in brief what it is. Then the second technique is the coding and interleaving. Okay, coding and interleaving. This also, I think, it is coding you have studied maybe in your sixth semester or fifth semester, information theory and coding as one subject. I expect you people to just name what are the different codes you have studied at least, right? The third one is the automatic repeat request, ARQ. Hope you have heard this name, ARQ, anywhere in your study so far. Automatic repeat request. Any one of you can say. I'm just asking, have you heard this name, ARQ, automatic repeat request? Yes. You have not heard the name ARQ?
No, sir.
No. Okay, fine. Okay, the next technique is the adaptive modulation and coding. Of course, you are aware of modulation, okay, both analog and as well as digital. Let us see what it is, adaptive modulation and coding. So these are the four different techniques which will be used for mitigating the narrowband fading. Okay, and to discuss about broadband fading. So again, there are four techniques. One is the spread spectrum and rake receivers. Okay, at least you have idea about the spread spectrum, which we have discussed in digital communication in the module 5, right? So with that basic knowledge, I think you will be able to understand in what it is and all. Then the next is equalization. Even this also I have discussed, which also studied in digital communication, equalizers, right? So next technique is the multi-carrier modulation. So under multi-carrier modulation, we will be discussing about OFDM. So how it will be able to mitigate the broadband fading, right? The next technique is single carrier modulation with frequency domain equalization. That is SC FDE, what we say. Okay. So these are the four different techniques which are used for mitigating the broadband fading. So hope you all aware what is narrowband fading and broadband fading. So when do we say it is broadband and when do we say it is narrowband, right? So when the symbol duration, okay, which we denote as a T, right, capital T, is much less than the delay spread. Okay, that is one case. Another case is what? When the symbol duration is much greater than the delay spread. Okay, so as I said, means we have discussed in the earlier classes how this frequency selective fading causes dispersion in time, right? Uh, which causes the adjacent symbols to interfere with each other, right? When until unless when the symbol time is much greater than the delay spread, right? So if the symbol time is less than the delay spread, definitely there will be an inter-symbol interference. So that leads to what a distortion, right? So let us see about the first one, that is the spatial diversity. Yeah. So this diversity is one of the uh, key technology or key technique, what we can say, which will be used to overcome the performance loss from the fading channels. Okay, and this diversity is also used to improve the packet error rate and as well as bit error rate. Okay, so diversity. So under diversity, so many types are there. So we will be discussing here one, that is the spatial diversity. Okay, hope I am clear what I am saying. Yes.
Yes, sir.
Yeah. Yeah, I said diversity is one of the key technique to overcome the performance loss from the fading channels, right? And this diversity is also used to improve the packet error rate and bit error rate. So without diversity, it is virtually impossible to visualize the high data rate in wireless communication. So diversity is must. Okay. So in that, the first thing is the spatial diversity, right? So as I said, it is one of the powerful form of diversity, and it is desirable because why spatial diversity is required is it will not necessitate the redundancy in time or frequency. Okay, so how do we achieve this spatial diversity, right? So the first thing is why it is so important is it does not necessitate the redundancy in time or frequency. Okay, and how do we achieve that? It is achieved by having two or more antennas at the receiver and the transmitter. So by this time, I hope you will be able to visualize that. So if I have two antennas at the transmitter side and two antennas at the receiver side, or one antenna at the transmitter side and two antennas at the receiver side, during that time also I can achieve the spatial diversity. Okay, so space diversity, as I said, consists of two receive antennas. So out of those two receive antennas, it will be receiving the signals, right? So it will take the stronger of the two signals. It will select the stronger of the two signals in case of spatial diversity. So that we call it as a selection diversity. So what is the selection diversity? As long as the antennas are spaced sufficiently, then the two received signals will undergo approximately uncorrelated fading. So if they are uncorrelated fading, right, then we call that as a selection diversity. So this spatial diversity, as I said, it will have receive antenna arrays, right? It may be two or more antennas at the transmitter and receiver side. So this spatial diversity will be selection combining, and the second one is maximal ratio combining, MRC. Okay, and this diversity can also be achieved with transmit diversity by using space-time codes and by using even transmit pre-coding and even other combinations of the transmit and receive diversity. So this is in brief what I said about the diversity. Hope at least you will be able to grasp and say what is diversity, right? So why it is used? It is used to overcome the performance loss from fading channels. At least you will be able to tell that much. And it is used to improve the packet error rate and bit error rate. Yes, hope I am clear.
Yes, sir.
Yeah,
Yes, sir.
at least you should be able to understand the purpose of diversity, right? So I said diversity is used to overcome the performance loss from fading channels. I hope you all know what is fading. So it is the random fluctuations of the signal is known as a fading, right? So why does it happens and all we have discussed, right? Because the wireless channel is not a free space, because so many obstructions will be there between transmitter and receiver. As I said, buildings will be there, trees will be there and all. So the signal will be received through multiple paths, right? With the reflection, scattering, and shadowing effects and all that. So because of that, there will be what? Uh, random fluctuations, right, in the received signal, that we call as a fading, right? So the diversity is the key technique. As I said, it is used to overcome the performance loss from fading channels, and it is also used to improve the packet error rate and bit error rate. Okay, so how do we achieve this spatial diversity? Spatial diversity will be achieved with two or more antennas at the transmitter receiver side, right? If those antennas are spaced properly, then it will be selecting the stronger of the two signals, right? And those two signals will be, as I said, they are uncorrelated. Okay, so with that, we will be able to achieve this uh, spatial diversity, right? So the techniques used are, one is selection combining and another one is maximal ratio combining, right? So transmit diversity is also another technique with the space-time codes used for this spatial diversity. Okay, and another thing is transmit pre-coding also, and a combination of these things. So I will just give an example here. So this diagram shows uh, the selection of diversity. Okay, how it will be able to eliminate the fading effect. So two signals are there. Hope you are able to see this diagram.
Yes, sir.
Yeah. So two signals are there. Two signals are there. Signal one with continuous line and signal two with dashed line. So as I said, it will be taking the best of these two, right? So which is written by a thick line, that is maximum of 1, 2 is written, right? So that by doing so, it is possible to overcome the fading. Okay, so by selecting the best of those two signals, it is possible to avoid the fading. And just to have a idea about diversity, I've shown here one diagram which we will be discussing in the, I think, next module. So just you can have a look. So transmitter side, one antenna is there, and at the receiver side, so multiple antennas are there, right? And these are H1, H2, and so on. Okay, HNR. So multiple channel gains are. So we will be selecting the best of one, right? So that is about the selection diversity. And another one, as I said, it is MRC, that is maximal ratio combining. So this is another technique to uh, improve the diversity. Okay, so here we use the weighting factors. Okay, by doing that, from the antenna there will be weighting factors. So by adjusting that, we will be able to get the maximum uncorrelated signal. So I think this much idea is enough here to say about spatial diversity. Okay, even you don't have to write this diagram, but if you write also, nothing wrong. Okay, so the picture will be clear about the spatial diversity. Okay, so these, with these two diagrams and that much of description, I can say I hope I conveyed what is the need of spatial diversity. Of course, with equations only we will be able to understand how the fading can be reduced with the use of multiple antennas at the receiver side or at the transmitter side, right? So just here I'm giving you a rough idea about the spatial diversity. Is that fine? Yes, I did not get any response.
Yes, sir.
Yeah, at least you should be able to write these two diagrams, and you should be able to say, okay, two signals are there. Out of these two signals, best one will be selected. Okay, so by doing that, we can say the fading will be avoided. Okay, so the next technique. Okay, next technique is the what? Coding and interleaving. Okay, hope you all studied a variety of codes in your information theory and coding. Okay, so even with the use of coding, we will be able to reduce the fading effects. Okay, so is it possible to say from your end what are the different codes you have studied in ITC? Yes, quickly, I expect you to respond. What are the different coding techniques you have studied? Okay, of course, you might have studied source coding techniques and as well as channel coding techniques. Here I'm asking you people to say about the channel coding techniques. Is it possible to mention the names? Just I'm asking the names, not the concept.
Hoffman coding.
Yes, anybody remembered anything?
Hoffman coding.
Hello? So nobody is remembered. One semester you people have studied about coding theory, information theory and coding. Yes, my dear students should respond. Either you say yes or no, then I can say from my end.
Block codes.
Okay, you people have studied about block codes. Yeah, whether it is a source coding technique or channel coding technique.
Channel coding techniques, sir.
Channel coding technique. Okay. Okay, fine. So as I said, the error correction codes. Okay. These error correction codes are also known as forward error correction. That is, we say FEC. Okay. So by using these error correction codes, or I said the forward error correction codes, we will be able to introduce the redundancy at the transmitter side. Okay, that will allow the receiver to recover the input signal even if the received signal is significantly degraded by attenuation, interference, and noise. Okay, so with the use of these error correction codes, right, it is possible to introduce the redundancy at the transmitter side, which will allow the receiver to recover the input signal even if the received signal is significantly degraded by attenuation, interference, and noise. Hope I am clear. Yes, I am asking, hope I am clear in that definition. With the use of, I said, error correction codes. I said error correction codes are also known as forward error correction. It is possible to introduce the redundancy at the transmitter, which will allow the receiver to recover the input signal even if the received signal is significantly degraded by attenuation, interference, and noise. I'm saying. Okay. See, what we do in source coding is we eliminate the redundant information. Right. With that, we say we are going to represent the information effectively. With that, we can save the bandwidth. But when it comes to the channel coding techniques, what we say, we introduce redundant bits. Okay, so that is under the control of design engineer. Okay, communication design engineer. So by adding controlled amount of redundant bits, right? So that we call as a channel coding, right? It is possible to achieve reliable communication. So what is that reliable communication? Is this? Okay, means we will be able to introduce the redundancy at the transmitter side, right? That will allow the receiver to recover the input signal even if the received signal is significantly degraded by these things. What are those things? It is degraded by attenuation. We all know why attenuation happens, right? Interference and noise. Yeah, of course, the coding rate what we use is less than 1. Right, that will be the inverse of the redundancy what we added. Means what I mean to say is here, if I say the coding rate is 1/3, okay, means what? We will be introducing 2 redundant bits, okay, for every original information bit. Hope you understand. Output of a rate 1/3, if I rate, that is code rate is 1/3 means I will be adding 2 redundant bits, okay, for every original information bit. Means if I have one information bit to be transmitted, for that I will be adding 2 redundant bits. So by adding 2 redundant bits, I will be able to overcome the fading effect, or I will be able to mitigate the fading in the channel over the information. Hope I am clear. Okay, so with well-designed error correction codes, which will increase the achieved data rate even when the coding rate is less than 1. Because, so why do we say even when the coding rate is less than 1? You may all get the doubt. For one information bit, we are adding 2 redundant bits, right? With that, even if the transmission rate is constant, right, we will not be able to convey much information, right? Because we are adding more redundant bits. Because for one bit I am adding 2 redundant bits. You may be thinking like that. Yes, of course, that is right. But how it will be, I am saying it is more reliable because with the redundant bits, right? If I am receiving the information for only one transmission in a better way compared to the transmission of the same signal for more than once, in that way, I can say I will be able to get more data rate. I don't know whether I could convey or not. I said even though the code rate is less than 1, because of the reliability, the number of bits per symbol that can be successfully transmitted will be increased by a factor greater than that coding rate. Okay, so that will leads to the net gain. Okay, the most popular type of encoders or codes used in LTE are the convolutional encoder at the transmitter side, and I hope Viterbi decoder is used at the receiver side. Okay. In addition to this convolutional encoder, even turbo codes are also used. Okay. So when do we use the turbo codes in LTEs? means with the use of turbo codes, it is possible to provide more resilience to the errors through the iterative decoding, I can say. Okay, so this is about coding. I said coding and also the interleaving. Okay, both can mitigate the effect of narrowband fading. Okay, yes, this is one example which is shown here to say that how convolutional codes. Okay, yes, you are not studied about convolutional code in your ITC.
Yes, sir.
Have you studied it? This convolutional code?
Yes, sir.
Okay, okay, then you don't have to worry too much about this diagram. Just I am showing here how this convolutional code is used in LTE for this broadcast channel, right? So this is the input sequence, means one bit I am giving here, right? I am able to get the output as 3 bits, okay, which is written in octal here, okay, 133 or 17 or 165. So it is in octal. We all know each octal digit will be replaced by how many binary digits? Any one of you can say quickly. Each octal digit can be represented by how many binary digits? I'm asking a very basic question.
3,
Yes,
sir.
you need. Huh?
So can you repeat the question?
I'm asking here. See, output bits are written in octal, right? Output of this convolutional encoder is written in octal. I said, I asked, each octal digit is represented by how many binary digits or bits?
3 bits, sir.
3 bits, right? So every octal digit will be represented by 3 binary digits, right? So in that case, here I have written 3 means it will be written 011. Again here 3 means 011, right? Then here 1 is 001. So that will be its equivalent binary, right? So hope I think we will be able to understand how many delay elements are there and what will be the constraint length, right? Constraint length of this code. I think here the constraint length of this code is 7. Okay, how many the elements are the memory elements we have? 6 memory elements, right? 6 memory elements. And then how do we tap these things, right? That depends on if it is 1, it will be tapped with the delay. If it is 0, no tapping, right? So I think I don't go in depth about this. Just I am saying how this convolutional coding is used in LTE for this broadcast channel. Okay, I think you can, with your basic understanding about ITC, you can just have a look about this. In the same way, so let me say how that Viterbi decoding is used, right? Viterbi decoding is used in LTE. This one I said, na, as a decoder, right? So this is your Viterbi decoder. Okay, and here means there is a parallel concatenation of codes. So with iterative decoding, we will be able to get the required outputs. Fine. So which is used in uplink and as well as downlink shared channels. So when we are discussing about the channels, we'll see how all these things will be working. Okay. Fine. So that is about coding. Just I briefed about coding, what it is, how it can mitigate the fading. Okay. Then what are the different types of codings used in LTE? Okay. Then when it comes to interleaving, so you all know what is interleaving? Any idea? Interleaving? You can tell the general meaning of interleaving now. Yes, interleaving. Yes, you can't tell the meaning of interleaving. Yes. No response. Interleaving. Yes, Pranav.
Yes, sir.
I'm asking what is interleaving, the meaning of interleaving. Okay, fine. So I will continue. So
Yes,
interleaving
sir.
is
Like
used.
we are mixing signals together, sir. Like digital signals alternately.
Alternate mixing of bits, we can say, right? Maybe a block of bits. Okay, maybe let us assume that 100 bits I have. I am uh, those 100 bits. I will be making it as a size of 10 bits of 10 rate, right? 10 bits. Those 10 packets. You can think I have 100 bits. I am dividing that into 10 bits of 10 packets. Those will be interleaved. Okay, and in between some other bits will be there. So that is known as the interleaving. Means I am shuffling. What I can say, shuffling. So the interleaving is nothing but a shuffling of the coded bits. So that will, by doing so, I will be able to improve the robustness. Okay. Okay. So by shuffling the coded bits, so which will improve the robustness to the burst errors. Okay. So why that burst errors will happen? That is caused by due to bursty noise or as well as interference, right? And even it may be due to the fading in time or frequency. So without interleaving, what happens? Because of that noise or fading, the adjacent bits in the transmitted signal will be degraded, right? So then it is becoming very difficult for the receiver, okay, to decode at the receiver side. So that is why we do the interleaving. With that, we will be able to improve the robustness due to the burst errors. Okay. Yeah. So what I mean to say is interleaving is nothing but spreading out the coded bits so that the effect of burst error will be minimized. Okay. And this is in case of conventional convolutional coding. But the purpose of interleaving in turbo coding is slightly different. Okay. The purpose of interleaving in turbo coding is used between the concatenated codes. Okay, so concatenated codes means what? One code is joined with another code, right? So that is provided. Uh, Means this interleaving is used to provide the statistical independence between the two encoder outputs. Okay, so with that, what I can say is interleaving is very effective in allowing error correction codes designed for constant, time invariant, additive noise channels, and also it works well on fading, time invariant noisy channels. Okay, so this is all about interleaving and coding, what I discussed so far. Okay, so the next one is the next technique, that is the third one, is the ARQ. So already you people said you are not aware of what is ARQ. I understand you might have studied this in your CCN, but you are saying no. Okay, it is fine. ARQ, that is automatic repeat request, is basically a MAC layer retransmission protocol. It is okay. I hope you understand what is MAC layer. Are you aware of MAC layer? Yes, my dear student,
Yes,
should
sir.
say. In which layer it will come? MAC layer?
Data link.
Data link layer, right? Good, very good. So what I wanted to say is this automatic repeat request is a MAC layer retransmission protocol. Okay, so it allows the erroneous packets to be quickly retransmitted. Okay, the purpose of ARQ is to allow the erroneous packets to be quickly retransmitted. So that is done by at the MAC layer. Okay. So this protocol means whatever the ERQ, what I am saying, okay, it is basically a protocol, right? So it works in conjunction with the physical layer error correction codes and as well as the parity checks to ensure reliable links even in the hostile channels. Fine. Means this ARQ works with the physical layer error correction codes. Okay, so there is a link. It is not completely independent. Okay, though it is there in MAC layer. Fine. So it works in conjunction with the physical layer error correction codes and as well as parity checks. Right. With that, it will be able to ensure reliable link. Okay, even in the hostile channels. Fine. So how does it works? Right. That may be your question. So what happens even if there is a single bit error? Okay, even if it is there, even if it is a single bit error in the packet. Okay, so what the receiver will do? It has to reject that, right? Because means if I hope you understand the packet will be consists of several bytes, right? So let us assume that 100 bits are there. Out of 100 bits, even if one bit is error, then it has to reject that complete packet, isn't it? So though 99 bits are correct, even if one bit is wrong or there is an error, it has to reject that, right? So here what happens with that? Okay, with this ARQ, the entire packet will be again retransmitted, right? Even if all bits are already received and correct, with because of one bit error, it has to again retransmit, right? That is the way the ARQ works. So we feel that it is an inefficient technique, because if it is retransmitting the same packet twice, there is a possibility of receiving, as I said, 99% of the bits are correct and only one bit is wrong. In both the cases, if I receive two packets, uh, then in one packet maybe one bit is wrong, another packet maybe another bit may be wrong. But when I combine that, so overall I will be able to identify where the error is, right? So retransmission of the same packet uh, again and again leads in inefficiency, right? So to overcome that problem, we go for hybrid ARQ. Okay, so what is that hybrid ARQ? It will combine the concept of this ARQ and as well as the forward error correction codes, right? As I said, no, in the previous case, that is in ARQ, it will be retransmitting the packets which are received in error, right? With that retransmission of same packet again and again leads to wastage of the resource, right? So in case of hybrid ARQ, what is done is it will be combining that ARQ technique plus forward error correction so that it can be avoided the wastage of the packets, right? How does it will improve the efficiency? So it will do, what it will do is, in case of hybrid ARQ, it will use the channel encoders, either it may be convolutional or turbo encoder, so which is used to generate the additional redundancy to the information bits. Okay, and another thing is, instead of transmitting all the encoded bits, okay, instead of transmitting all the encoded bits, only the fraction of the encoded bits will be transmitted here. This is important, what I can say. In case of hybrid ARQ, it will not transmit all the encoded bits. Okay, it will transmit only a fraction of the encoded bits, right? So with that, what happens? Okay, so by doing so, means how do we say it is transmitting only the fraction of the encoded bits? So that we call as punctured bits. Okay, so that is achieved by puncturing some of the encoded bits to create an effective code rate which is greater than the native code rate of the encoder. I don't know whether I heard about this puncturing. Puncturing means we will be removing some of the bits at the output side. Okay, so I can give an analogy of just removing the air of a uh, air in the tire of a vehicle. Okay, when we remove some amount of air, what happens? The vehicle cannot move further, no, or cannot move much faster, right? Like that. So we remove some of the bits. So after transmitting the encoded and punctured bits, the transmitter will wait for the acknowledgement from the receiver side, right? Uh, just telling that whether the receiver is able to successfully decode the information bits from the transmission. Once the receiver intimates that yes, it could decode all the information properly, then nothing will be done. If the receiver is unable to decode the information bit, then what the transmitter will do, it will resend another copy of the encoded bits. By doing so, we will be able to improve the efficiency of the packet transmission. That is what happens in hybrid ARQ. Okay. So in brief, I said what is hybrid ARQ? It combines the concept of ARQ and as well as forward error correction codes. Okay, I said it uses the channel encoder to generate the redundancy to the information bits, right? So what it will do is, instead of transmitting all the encoded bits, it will be transmitting only the fraction of the encoded bits. So by doing so, what happens? The transmitter will be waiting for the acknowledgement from the receiver, saying that whether the receiver is able to successfully decode the information bits from the transmission or not. So if the receiver is able to decode the information bits, then nothing will be transmitted from receiver to transmitter. Okay. Otherwise, the receiver, if the receiver is unable to decode the information bits, then the transmitter will be resending another copy of the encoded bits. Right. So with that, I said it will be able to improve the efficiency of the packet error rate. Means we will be able to improve the packet transmission. So here two types of hybrid ARQ techniques are there. One is type 1, that we call it as chase combining, and another one is type 2. Okay, the type 2 is known as the incremental redundancy. Fine. So what is this type 1 hybrid ARQ? This type 1 hybrid ARQ, I said it is also known as chase combining, right? So here what happens during the retransmission, the transmitter will be sending a copy of the encoded bits. Okay, so that is identical to the first transmission, and the receiver does the soft combining and received bits with the previous transmission. Hope you are aware of soft combining. And two types of combining are there in the receiver. One is soft combining and is hard combining. So here I said it will be doing the soft combining the received bits with the previous transmission, right? So with that, what happens? The encoded bits are the same in all the transmissions, and the noise or interference will be uncorrelated. With that, the receiver can combine all the transmissions to increase the effective signal to interference noise ratio. So with that, it will be improving the performance. The second thing is, yeah, I said for every subsequent transmission, the error probability will be reduced, and this process continues until the receiver is able to decode the information without any errors. Okay, so that is all about the chase combining. So I repeat once again, what happens in type 1 hybrid ARQ? I said that type 1 hybrid ARQ is also known as chase combining. Here, during the retransmission, the transmitter will be sending a copy of the encoded bits that is identical to the first transmission, right? And the receiver soft combines the received bits with the previous transmission. So by doing so, what happens? The encoded bits are the same in all the transmissions, and the noise is uncorrelated, right? So the receiver can combine all the transmissions to increase the effective signal to interference noise ratio. So with this, right? So every subsequent transmission, the error probability will be reduced, and this process continues until the receiver is able to decode the information without errors. That is in type 1. So in case of type 2 hybrid ARQ, as I said, it is also known as incremental redundancy. Here what happens, the transmitter changes the bits, okay, that are punctured during the retransmission. Okay, so with every retransmission, the effective code rate at the receiver will be decreasing, which will reduce the error probability. So that is what is known as incremental redundancy. So what happens in case of incremental redundancy? The transmitter changes the bits that are punctured during a retransmission. I said what do you mean by punctured bits, right? So punctured bits means removing some of the bits, that is the output coded bits are simply dropped, what I can say. Okay, uh, why do we want to drop the output coded bits? To lower the transmission rate, that we call it as a punctured bits or puncturing. Okay, so with that, what I can say is, in case of incremental redundancy, the transmitter will be changing the bits that are punctured during the retransmission. So with every retransmission, it will increase the effective code rate at the receiver. That will reduce the error probability. So this is all about the ARQ, hybrid and as well as simple ARQ. And we will be discussing about again ARQ in detail, maybe in the module 4 or 5. Okay, so it is a just introductory, what I can say. Fine. If you have idea about how packet transmission happens, I think you will be able to. I think are you aware of slotted aloha and pure aloha? Yes.
Yes, sir.
So you should be able to correlate those concepts with this ARQ. At least, is it possible to say what I said in ARQ? I don't know whether I went fast or slow. ARQ. Is it possible to say what is done in ARQ? I said it is basically, I repeat once again because it is an important concept. ARQ means what? Automatic repeat request. It is a MAC layer retransmission protocol. Okay, at least you should be able to say what is ARQ. ARQ is a MAC layer retransmission protocol. So it allows erroneous packets to be quickly retransmitted. Okay, ARQ allows erroneous packets to be quickly retransmitted. Okay, I said this protocol works in conjunction with physical layer error correction codes and as well as the parity check codes to ensure reliable link even in hostile channels. Okay, so a single bit error causes a packet error. Okay, with ARQ, the entire packet must be retransmitted, even when nearly all of the bits already received were correct. So, which leads to inefficiency, I said. Right? And I gave an example that if out of if 100 bits are there, out of 100 bits, if I receive 99 bits correctly and only one bit is wrong, right? Again, it requests for retransmission of the same packet, right? If it is received second time, even for second time also, if I receive 99 bits properly and one bit is in error, right? Again, it will go for retransmission, right? So by doing so, it leads to inefficiency, right? So what hybrid ARQ will do is, it will be combining the concept of this ARQ and as well as forward error correction. By doing so, means it is possible to avoid, as I said, in the previous case, in ARQ, it will be wasting the resource, right? By combining the received packets, means it will do the combining of those received packets, it will do some XOR operation, right? Then it takes care of that retransmission, right? So in hybrid ARQ, the channel encoder, whether it is a convolutional or turbo, is used to generate additional redundancy to the information bits. So what here is done is, instead of transmitting all the encoded bits, that encoded bits are what? Systematic bits plus redundancy bits, it will be transmitting only a fraction of the encoded bits. So by doing so, it is possible to achieve or create an effective code rate which is greater than the native code rate of the encoder. Okay, and as I said, in hybrid ARQ, the transmitter will be waiting for the acknowledgement from the receiver whether the receiver was able to decode the information correctly or not. Okay, then only it will do the retransmission, otherwise it will not. So if the receiver says yes, all the informations are decoded properly, then it won't transmit. If the receiver is unable to decode information bits, then what the transmitter will do, it will resend another copy of the encoded bits, not the entire packet. Hope you are clear. In the ARQ, entire packet used to be transmitted, retransmitted. But in case of hybrid ARQ, by doing or with the combining use of that forward direction codes, the bits will be encoded. Okay, only a fraction of the encoded bits will be retransmitted, not the entire packet. Okay, so with that, I can say we will be able to improve the efficiency of transmission. And I said again, there are two types of hybrid ARQ. One is type 1 and another one is type 2. So type 1 hybrid ARQ is known as chase combining. So what is done in chase combining, I said, here what happens during the retransmission, the transmitter will send the copy of the encoded bits that is identical to the first transmission, and the receiver will soft combine the received bits with the previous transmission. So the encoded bits are the same in all the transmissions and the noise is uncorrelated, right? So the receiver can combine all the transmissions to increase the effective signal to interference noise ratio. So with that, means with every subsequent transmission, the error probability will be reduced, and that this process will be continuing until the receiver is able to decode the information without any error. So in case of type 2 hybrid ARQ, as I said, it is also known as incremental redundancy. What happens here? The transmitter changes the bits that are punctured during a retransmission. So with every retransmission, the effective code rate at the receiver will be decreasing, with which will reduce the error probability. Okay, so I think by taking example, we will be able to understand or get the clear picture of this, not just by saying the process. So let me try that taking some example, maybe in the upcoming lectures, not now. Okay, just I wanted to convey here what is what. Is that fine? So the next one is adaptive modulation and coding. I think let me take up that in the next class, that is in the afternoon. Okay, so with that, if you have any questions to ask, you can ask, because I keep talking last maybe 55 minutes without giving much gap, asking few questions here and there. Yes, is it clear? Have you understood whatever I said? Is it possible to just sum up what I discussed today? Yes, Abhilash, quickly in 2 minutes. Abhilash.
Yes, sir.
Yeah, can you just brief or summarize what I discussed today?
Sir, initially we discussed about the narrowband fading,
Yeah.
and then regarding coding and interleaving,
Okay.
and we discussed about ARQ, then type 1, type 2.
Okay. You joined late or what?
Sir, like 5 minutes, sir.
5 minutes. Okay, then you are not aware of diversity.
Diversity. So yes, sir.
You are there for diversity when I was discussing about spatial diversity.
So actually, from my end, at that time, the connectivity was not great, sir. So I was only
Uh,
able to hear few of the things, sir.
okay, okay, fine. Okay, fine. Yes, what is your understanding about at least coding and interleaving?
Um, so basically, interleaving is when we have to add correction bits.
Interleaving, no man, no correction bits we are adding. It is a shuffling of encoded bits. That's
Sorry,
all.
shuffling of the encoded bits. So,
Mm. Yeah, coding.
coding, sir, like
Mm.
we discussed about sir, error correction codes.
Yeah, I did
That
not
is
discuss anything about error correction code. Just I told the importance of that error correction
error
codes.
correction. Yes, sir.
Okay, error correction codes is also known as
Forward error correction.
forward error correction, that is FEC.
FEC.
So, so the use of these error correction codes, right, will
Yes, sir.
introduce redundancy at the transmitter. Okay,
Yes, sir.
so that will allow the receiver to receive the signal, even though if the received signal is affected by attenuation, noise, and interference. Okay,
Yes, sir.
yeah, because it is adding redundancy. Means the error correction codes or forward error correction code will be adding the redundancy at the transmitter. Okay, that will allow the receiver to receive the received signal. Means it will be able to recover the received signal even though the received signal is affected by noise, interference, and attenuation. Okay, fine. Yes, Madhura, can you tell what are the different codes used in LTE? I said encoder and decoder. Madhura. Yes, Madhura is not talking. What about Aditya Datta? Yes, Aditya Datta.
From
Hmm.
CR channel coding, sorry.
Yeah, what are the, at least name, you can name it, no? What codes I said, what codes are used in LTE? Encoder, man. See, it is names. Why you can't catch the names? Convolutional encoder, I said, then turbo encoder, right? Then Viterbi decoder is used at the receiver side. Okay, fine. I think with this, let me stop. Let me take the attendance. I hope I will be able to see you all in the afternoon because